Assalamu alaikum, dear students. As you know, we are working on the unit number 12 from your text context, and the name of the chapter is electromagnetism. We already have done some topics of this chapter. Now we will proceed to the over next topics, the relevant next topics. Okay, Bismillahirrahmanirrahim. Let us proceed further. Okay, today topic that we are going to cover from the unit number 12 are the motion of the charged particles in the uniform magnetic field. Then the second topic will be the velocity selector method, and the third one will be the magnetic field patterns. Different types of the magnetic field, how they look like, and how is the magnitude of the magnetic induction or the magnetic flux density there. Okay, now come to the basic one. First topic, that is the motion of the charged particles in the uniform magnetic field. Okay, we here you can see a picture, right? It's a diagram. You remember what does it show? It shows the trajectory of a charged particles in a magnetic field. Can you just share what type of the magnetic field is it there? That is an inward magnetic field. That is, it is directed from you towards the paper. It is away from you, right away from you within the paper, into the paper, right? And the red arrows there, they are showing the direction of the force, which is perpendicular to the plane where the velocity and the B, that is the magnetic flux density, is there, or the magnetic strength, or the magnetic, you can say magnetic induction is there. F is perpendicular to both B and V. B is the, as I have earlier told you, that is the magnitude, or the, you can say that is a magnetic induction vector or the magnetic strength vector. And V is the velocity of the charged particles there, the tangential velocity, translational tangential velocity. And F is the magnetic force there. You can see the trajectory is a circle. It means there must be a centripetal force. That is the key concept. If the charge is moving when V and B are perpendicular to each other, then what will happen? The particle will move in a circular direction or the circular trajectory, right? And if it is moving in a circular trajectory, then it means that there is some centripetal force involved. Let us analyze that force and see what are the outcomes. Okay, when you have to find the radius, as you have seen the picture earlier, and there is a diagram again on the page. Look, the inward force that is seem to be inward, but that is perpendicular to both V and B vectors. Okay, the velocity and the magnetic field strength, or the magnetic field induction vector. Okay, if this F is perpendicular to both of them, right? And this is actually the magnetic force there. We have seen that in the previous chapter that we read yesterday, we discussed that the magnetic force is equal to QVB. And in the vector form, we say Q multiplied with the V cross B, right? That was the magnetic force there. Okay, if the particle is moving in a circular trajectory, then that means there must be a centripetal force involved, as you can see, right? Small m is the mass, V is the velocity, the translational velocity of that particle, and R is the radius of the circle in which the particle is moving, right? And the expression 2, as you can see, that is about a centripetal force, which is actually providing the necessary, the magnetic force is actually providing the necessary centripetal force there, राइट इट मस्ट बी इक्वल. देखें सेंट्रीपिटल फोर्स को कुछ ना कुछ सोर्स चाहिए. देयर अ फोर्स, रेलिवेंट फोर्स विच एक्चुअली प्रोवाइड्स द नेसेसरी सेंट्रीपिटल फोर्स. और यहाँ पे सेंट्रीपिटल फोर्स अगर बॉडी सर्कल में मूव कर रही है तो उसको सेंट्रीपिटल फोर्स कौन प्रोवाइड कर रहा है? एक्चुअली द मैग्नेटिक फोर्स इटसेल्फ, QVB जो फोर्स है, इट इज़ एक्चुअली प्रोवाइडिंग द सेंट्रीपिटल फोर्स, right? So the both forces will be equal. So this is the key concept I was talking about, that if we have discovered and you have understood that which force or two forces are equivalent there, that is the magnetic force and the centripetal force. Okay, As the magnetic force is equal to the centripetal force, put in the values of both. Mv square over r is the centripetal force, and qvb on the right hand side is actually the magnetic force. This is the very key equation. It will provide us the remaining parameters. That is, what are the remaining parameters? Okay, the remaining parameter is the velocity. This equation, as you can see there, this equation will provide you, not equation 3, the beneath one, the resultant equation, mv square over r is equal to qvb. This equation is going to provide you the r, that is the radius of the trajectory in which the particle is moving, right? And then from this value of the r, you can find the angular frequency. If you do remember, in the fourth unit, most probably we read that this, for a velocity, v is equal to r omega, right? Omega is the angular frequency. Do you remember those equations, radial equations? V is equal to r omega, and as we have from the expression 4 there, as from the expression 4 there, we have manipulated the value for the r, then put in the equation, given equation in the equation 4, what you will get is r omega is equal to this one. From there, you will get the value for the angular frequency, right? This is what, first we evaluated the radius of the trajectory, then we evaluated the angular frequency. Now we will find the time period. Time period is equal here, is equal to 2 pi over omega. अब आपने परेशान नहीं होना, you won't get confused inshallah that from where do we have acquired that formula. बेटा असल में आपको पता है frequency और time period आपस में reciprocal होते हैं. As but this frequency is not an ordinary frequency, rather it is an angular frequency. Now as a radial angular frequency, the time period is equal to 2 pi, which shows for a complete cycle, and omega shows the angular frequency there. Right? In the linear relation, we say that t is equal to 1 over f, लेकिन क्योंकि ये रेडियल वैल्यूज में है, रेडियल कोऑर्डिनेट्स में, तो हम कहते हैं t is equal to 2 pi over omega. नाउ ओमेगा की वैल्यू आपने यहाँ से जो इक्वेशन 5 में है अभी फाइंड की है, आप जब इसमें वैल्यूएट करेंगे, यू विल पुट इन देयर एंड यू विल गेट द एक्सप्रेशन फॉर द टाइम पीरियड, राइट? दैट इज इक्वेशन 6, in which we have only evaluated, put in the value of omega, that is the angular frequency there. As you know, अब ये तो हमारे पास टाइम पीरियड है फॉर द एंगुलर फ्रीक्वेंसी, बट द टाइम पीरियड इज सेम. अब आप इस टाइम पीरियड का जब रेसिप्रोकल लेंगे, व्हाट विल यू गेट? द फ्रीक्वेंसी. आपको पता है कि फ्रीक्वेंसी इज द रेसिप्रोकल ऑफ द टाइम पीरियड. नाउ द इक्वेशन 6 विल बी रिवर्टेड, राइट? The reciprocal is equal to the frequency. We title this frequency as cyclotron frequency. Cyclotron is basically a particle accelerator which use this frequency. So the frequency entitled as cyclotron frequency, particle moves with the frequency in a cyclotron. So we are done with the first topic for today. Now we will approach towards the velocity selector method. Okay, that is a method in which we do separate some particles by differentiating the velocities. Like if a source has many charged particles, we can separate different particles by using the rule of the velocity, or they will all have different velocities. राइट? इस प्रिंसिपल को आपने यूज़ करना है. एक्चुअली होगा क्या? यू विल फर्स्ट सी, एज यू कैन सी इन द ऑन द स्लाइड, दैट यू विल फर्स्ट see animation I have prepared, right? By understanding that animation, it will be easy for you to apprehend the new concepts which are related to the velocity selector method. You can see a particle which is moving with a particular velocity enters in an electric field. This electric field will in fact put a electric force on it, whose value is given as QE, as you can see. Right? What this force will do, it will move the particle in the direction of the electric field like this. Now take the same particle and enter it within an magnetic field. What will happen there? this electric magnetic field will put a force on it, value is given as V cross B, and move it in the direction of the magnetic field, that is a circular direction. Why do you know why this particle is moving circular? Because the velocity and the magnetic field are perpendicular to each other. Now both fields are there, electric and the magnetic. You see the two forces are there. If the two forces are equal, then there will be no deflection, right? And by combining these for the undeflected particles, we will get an expression for the velocity. As you can see, how Q will be cancelled out. And the expression for the velocity is a ratio between the electric and the magnetic field there. Okay, this is for the undeflected particles. You can see? Okay, what if the magnetic force is greater? Then the particle will move in the direction of the magnetic field. And here, the velocity is greater than the ratio. And if the velocity is less than the ratio, then the particle will move in the direction of the electric field. Here you can see, right? There are the three conditions, one for the undeflected particles, and one for the dominating magnetic field, and one for the dominating electric field. These are undeflected particles. Right? And what about the others? The upper one are where the magnetic force is greater and the okay. As earlier you have seen the animation, and now we will understand the context of this animation. As you can see, when a particle, say a positive charge, a unit positive charge is entered in a combined electric and the magnetic field, what happens to it? Magnetic field will move it within the circle if the velocity and the magnetic field are perpendicular to each other. We have repeated this concept multiple times, so you must be an adept on it now. Okay, what happens? A unit positive charge enters in a combined electric and magnetic field, right? Some particles will get deflected on the P plate, which is actually the result of a magnetic force acting on it. And some particles, as beneath you can see, will collect on the plate Q, which have actually the electric field stronger, or under the influence of the strong electric field, there will be some particles will be deflected towards the point Q, and some will stay undeflected. Which will stay undeflected, for which the electrical force, electrostatic force is actually equal to the magnetic force. So the resultant will be 0. No force will act on these deflected particles, so they won't get any deflection, and rather they will move undeflected straight away. Right? So the particles of the different velocities are separated there, and if you have seen the animation prior to it, you will understand the concept very well. Okay, now let us proceed to the mathematical portion of this one. Velocity selector, it uses the perpendicular electric and magnetic fields to allow only the particles with a specific speed, as we are working on the velocity. So with a specific speed to pass through undeflected, right? The electrical force there is equal to QE. ये एक्सप्रेशन आपने पढ़ा था इलेक्ट्रोस्टैटिक्स में, यूनिट नंबर 10 में. ये आपने FE की वैल्यू बार बार जो हम यूज़ कर रहे हैं वहाँ आपने पढ़ी थी. देन द मैग्नेटिक फोर्स इज आल्सो एक्टिंग ऑन इट, क्योंकि इसी के अंदर मैग्नेटिक फील्ड भी है, सो दैट विल बी इक्वल टू FB. मैग्नेटिक फोर्स इज इक्वल टू Q इंटू V क्रॉस B. ये आपने कल पढ़ा था, ठीक है. एंड फॉर undeflected particles, these two forces will be equal for undeflected, not those that are collected on the P or nor those that are collected on the Q, rather the undeflected particles in which that are moving in a straight line they are not deflected to any angle, is equal in the magnitude, and it is opposite in the direction, they cancel each other. Fe is equal to Fb there. Okay, when you put in the values of Fe, you know Fe value is QE and Fb value is QVB, right? You will get the expression for the velocity, as you can see in the equation 1. In the animated video, you also saw that this is expression for the velocity for which particles that are not deflected anymore. Okay, okay, what happens to the other one? Let's see. If the velocity is greater than this ratio, E over B, E is for the electric field and B is for the magnetic field. If V is equal to this one, the particles will be actually undeflected. And if V is greater for the slower particles means that which have a low value of V, slower particles, they will be deflected in the direction of the electric force. And the faster part, ये इसका लॉजिक और भी है, स्लो पार्टिकल्स जो हैं उनकी वेलोसिटी कम है। कल आपने पढ़ा था कि फोर्स भी कम होगी, बिकॉज फोर्स डिपेंड्स अपॉन द मैग्नेटिक फोर्स एक्चुअली डिपेंड्स ऑन V and B. For slow particles, for low value of the V, the magnetic force will be weaker. इसलिए dominate कौन करेगा? Electrical force, and electrical force will deflect it in the direction of the electric field. Faster particles will be deflected in the direction of the magnetic force. Why? Because a greater value of the V means greater force, so it will push it towards the magnetic force. Okay, there is another force defined there which is called as the Lorentz force. Lorentz force जो है एक्चुअली ये वर्क करती है। मैग्नेटिक फोर्स जो है सर्कुलर पाथवे में अगर पार्टिकल मूव कर रहा है तो वर्क डन नहीं करती। लॉरेंट्स फोर्स इज एन एक्टिव फोर्स, अप्लाइड फोर्स है, एंड दैट इज अ सम ऑफ द इलेक्ट्रिकल फोर्स प्लस द मैग्नेटिक फोर्स F. जब आप वैल्यू स्प्लिट करेंगे यू विल गेट द वैल्यू फॉर द लॉरेंट्स फोर्स देयर, दैट F इज इक्वल टू Q इज, यू सी दैट इज फॉर द electrostatic force, and Q into V cross B, that is for the magnetic force. This equation shows that the combined effect of the both fields on a charged particles. We are done with the topic 2. Okay, now let us move towards our third topic for today, that is the magnetic field patterns. Right, what sort of the patterns are made in these phenomena? Let us see. Beta, current carrying straight conductor, we have priorly discussed that one. In the previous lessons we saw that a charged particle which moves will always have a magnetic field along with its electric field, right? And what will be the direction of the magnetic field? We saw that was in the form of the concentric spheres, and if you find the direction you will use the right hand rule. ये जो आपको फिगर नज़र आ रही है that is about how to use the right hand rule. इसमें हम क्या करते हैं, हम करंट की डायरेक्शन अपने थंब को देते हैं, तो the will of the finger will show you in which direction the magnetic field is working on, right? आप देख रहे हैं ना करंट की डायरेक्शन ऑनवर्ड है तो थंब को उसकी डायरेक्शन दी हुई है, तो विल ऑफ द फिंगर क्या बता रही है, दैट इट इज़ क्लॉकवाइज और एंटी क्लॉकवाइज, वो अपने आप उससे हिसाब लगा लें। एक्चुअली दिस हैज़ बीन ऑब्जर्व्ड, ये जो साथ आपको फिगर नज़र आ रही है, इन रियलिटी इफ़ द आयरन पार्टिकल्स आर प्लेस्ड अराउंड दैट कंडक्टर तो वो इस तरह से कंसेंट्रिक स्फीयर्स की फॉर्म में रेंज होना शुरू हो जाएंगे। ठीक है, ओके। दिस मैथमेटिकली हम कहते हैं B इज इक्वल टू म्यू नॉट I over 2 pi R. 2 pi R actually that will be the circumference of the magnetic field line that we are actually understanding. And what is I? I is the current which is passing through the conductor, and mu naught is a new constant. It is actually the constant of proportionality, and its name is it is permeability of the free space. We have read about the permittivity in the electrostatic concept, permissibility for the free space as well, and there is another constant mu naught that is actually what we call as the permeability. It is actually this constant tells that how many magnetic lines can pass through the free space, right? As a unit for the magnetic field is, we read that yesterday, you remember capital B, and the unit is Tesla. Okay. Second, we see now you bend the same conductor that was in there in a circular form, you will form a loop, And how is the field of a loop? It is equal to this one, as you can see in the expression, that is mu naught I over 2r. अब देखिए इसमें पाई गुम हो गया, ठीक है, पाई इसके लिए था और इसके लिए क्या था, b इज इक्वल टू म्यू नॉट आई ओवर 2r एंड n इज द नंबर ऑफ द टर्न्स, यानी एक लूप भी हो सकता है, मल्टीपल लूप्स भी हो सकते हैं, एंड एक्चुअली शोज द नंबर ऑफ द टर्न्स देयर, ठीक है। अगर आप राइट हैंड रूल यूज़ करेंगे, राइट हैंड रूल हेयर, it will actually suggest that if it is acting like a magnet, then where is the north pole and where is the south pole, right? And the field is stronger, yaad rakhein, field is stronger in the midst part of it. Where is the midst part? That is, you can see N and S. Here you can see the middle part of the loop. Here the field is strongest. Why? Because the both clockwise and the anti-clockwise magnetic lines, they will support each other exactly in the middle. On the fringes, the field will be weaker one, and in the middle it is a strong one. And actually, how does it seem like? ये भी आप देखें. I have suggested how it should look like. ये सर्कल्स कैसे होंगे? आपको पता है सबसे ज़्यादा मैग्नेटिक लाइंस आपको कहाँ नज़र आ रही हैं? दरमियान में. So their field will be stronger there, as the magnetic field lines are dense there. Okay, the last one is actually a solenoid. Solenoid, what actually is a solenoid? Solenoid is, it is actually the turn or the bending of those wire in a helical way, like a spring, right? उसको हम क्या बोलते हैं? दैट इज सोलिनॉइड. आप पढ़ चुके हैं इसको, मैट्रिक में भी सोलिनॉइड का कंसेप्ट आपने पढ़ा था. बी इज इक्वल टू म्यू नॉट इंटू एन आई इज द वैल्यू फॉर द मैग्नीट्यूड देयर. n over l is actually the number of the turns there, actually per unit length, यानी कितनी लेंथ के लिए सोलिनॉइड था, उसमें कितनी टर्न्स हैं, दैट एक्चुअली सजेस्ट यू द स्मॉल n द नंबर ऑफ द टर्न्स. और b आपने देख लिया है. अच्छा, आप सजेस्ट करेंगे, व्हाट डू यू थिंक द field is stronger and where the field will be weaker? ये एज अ असाइनमेंट या आप समझ लें आपके ऊपर छोड़ दिया ये चीज़. लेकिन अगर आपने डायरेक्शन फाइंड करनी है एंड यू वांट टू कंसिडर इट एज अ बार मैग्नेट, ठीक है, तो देन हम किस तरह फाइंड करेंगे? यू विल टर्न योर फिंगर्स इन द डायरेक्शन ऑफ द करंट. देखिए करंट ही इसके वायर के अंदर मूव कर रही है, ठीक है. ओके, अगर करंट मूव कर रही है देन ऑब्वियसली दिस सोलिनॉइड विल एक्ट एज अ बार मैग्नेट. तो जो आपके थंब की डायरेक्शन होगी, इट विल एक्चुअली सजेस्ट यू द नॉर्थ पोल. जैसे बार मैग्नेट का नॉर्थ पोल होता है, यहाँ पे भी आपको इसी तरह से नॉर्थ पोल उसका मिलेगा, ठीक है. द अपोजिट विच इज़ नॉट थंब की तरफ नहीं है, जो हम उसको क्या बोलेंगे, उस पोल को हम टाइटल करेंगे एज साउथ. और ये देखने में कैसा लगता है? एक्चुअली इट सीम्स लाइक दिस. ये आप देख रहे हैं, और यहाँ पे भी आपको नज़र तो आ रहा होगा कि मैग्नेटिक फील्ड लाइंस डेंस कहाँ पर है. जहाँ डेंस होंगी वहाँ पे फील्ड स्ट्रांग होगी. ओके, दैट इज़ ऑल फॉर टुडे. हैप्पी लर्निंग्स एंड स्टे ब्लेस्ड.